Greetings everyone. So now we are going to discuss about the basics of thermodynamics. First, we need to understand that what thermodynamic is meant by. Thermodynamics is basically the field of heat. It is a field of uh, it is a branch of physics in which it is a branch of physics in which we study about the conversion. It is in which we study about the transfer of energy from one form to another, from one body, sorry, it's not one form but it's the one body, from one body to another, either through heat transfer or through work done, such that if we do work if we do work on a body, then its internal energy either increases or decreases, and if we transfer heat from one body to another body, then its internal energy either increases or decreases. And that study of the transfer of energy from one system, from one body to another body through heat transfer or work done, is equal to the study of thermodynamics. Or in other words, we can also say thermodynamics is a study of the thermodynamics is the study of the transfer of thermal energy from one body to another body, which results in an increase in internal energy or results in the work done on or by the system. So this is what we study in thermodynamics. When it comes to the basic principles, we define two major things in thermodynamics as the thermodynamic number one as the thermodynamic system, and second is the thermodynamic surroundings. The thermodynamic system is any uh, part of the universe, is any part, is anything which is being observed. That's thing, that body, that structure can be considered as a system, while anything which is not included in our system, anything which is excluding our system, is known as the surrounding. And a system is separated from its surrounding by the help of a line, by the help of a line which is known as the boundary. And that boundary can be imaginary as well as it can be physical. Let's suppose if you are observing the system which is present in this piston, then at that moment the walls of the piston serve as the physical boundaries, and the area till which the system the volume of the system is present is known as the imaginary boundary, which is not existing in physical world, but it is imaginarily created a boundary for us. Now, if we talk about thermodynamic variables, before discussing that, we need to understand thermodynamic processes and what are thermodynamic processes. Whenever there is a change in a system, whenever there is a change in a system through several through change in either temperature, pressure, volume, or any other sort of thermodynamic variable, then it is not a thermodynamic process. Now, when it comes to the thermodynamic variable are those processes which are present uh, in a system, and the variation of those uh, on the variation of those principles, on the variation of those variables, we can change the state of the system. For example, if we change the pressure of a system, then the state of the system is changed. Volume of the system is changed, state of the pressure the system is changed. Temperature of the system is changed, state of the system is changed. Internal energy of the system is changed, state of the system is changed. Due to which any variable which causes a change in the state of the system by changing its value is known as the thermodynamic variable. Now, thermodynamic variables are state functions. These are state functions, which means they do not depend on their absolute value. Just like potential energy, it does not depend on absolute value, rather, it depends on the initial and final path. They do not depend upon the uh, path taken by the variable to complete. Rather, it depends on the difference of the initial and final path, due to which we always take the value of thermodynamic variables in difference. For example, if you want to take the value of thermodynamic variable for volume, we calculate the change in volume rather than calculating the absolute value of volume. For measuring the internal energy, we use a change in internal energy, which is represented by del U equal to U2 minus U1. Likewise, if we want to find entropy, we find change in entropy rather than getting its absolute value. So this is the major thing in thermodynamics, thermodynamic variables and thermodynamic processes. When it comes to the thermodynamic processes, there are two major thermodynamic processes. Number one includes renewable process, and number two includes non-renewable process. Renewable process is the one in which the process which has been done due to a change in the state of the system the process which has done due to the change in the state of the system can be reversed back exactly to the previous or initial state of the system. For example, if we melt ice, right? If we melt ice, then at that moment we can, when ice is converted into water, we can convert water back into ice by cooling it or putting it in a refrigerator or decreasing its temperature, due to which this process would be renewable process. But in practical terms, there is no process which is 100% renewable. 100% renewable or ideally renewable process does not exist. When it comes to the non-renewable process is the one which cannot be reversed back once it is done. For example, if we talk about the burning of uh, carbon, sorry, burning of glucose, burning of any sort of sugar. So when we burn the sugar, then burning of sugar will cause to create a black carbon ash, which would not be able to be converted back into the sugar, which is a non-renewable thermodynamic process. So in that sense, these are some basic examples in which we understand the thermodynamic variables. Now, when it comes to some other points that I would like to highlight over here is about types of system. We study thermodynamics in systems. So which system needs to be there and what are the types of system in actual? So there are three systems which are studied in thermodynamics. Number one is open system. Let me just type that down. Number one is open system. Within an open system, there's transfer of matter as well as transfer of energy possible. Number two is a closed system. Whenever we study thermodynamics, we utilize closed system because it is the system which involves transfer of energy, but it does not involve the transfer of matter. It involves transfer of energy but does not involve transfer of matter. Likewise, if we talk about an isolated system, which is the third type, it is a system in which neither energy can go in or out, nor the matter can go in or out of the isolated system, due to which isolated system is 100% isolated system does not exist. 100% isolated system does not exist on earth particularly. While when it comes to closed system, we have many examples of closed system which are done in modernized laboratories. Open system is around everywhere. If we do a random chemical reaction in open air, then it's simply considered as an open system. Closed system in which if we are taking, let's suppose, a jar, and we are not allowing the transfer of matter inside it, and rather, allowing the transfer of energy, then it is a closed system. A good example of this is pressure cooker. On the other side, if we talk about isolated system, the isolated system is the one which can be given as an example of thermoflask. Thermoflask is not 100% isolated system because it's due to some it's not 100% isolated because from after some time when we put something cold or hot into it, the temperature starts to decrease or increase, because energy is being transferred in some manner, right? As I previously mentioned, 100% isolated system do not exist. So these are the types of system as well. Now, after discussing this, we'll be now moving forward with the internal energy. what is meant by the term internal energy. So when we um, divide energy into two major types, there are two major types of energy. Number one is kinetic energy, and number two is potential energy. Kinetic energy and potential energy, right? So if we talk about macroscopic level, we study thermodynamics on macroscopic level, which means we study the state of the molecule, uh, we study the state of the system rather than the state of the molecule. We do not study what the molecule as an individual molecule is doing, but we study the state of the system. State of the system is what the system as a whole is having uh, in it. So state of the system is studied in thermodynamics, which means we consider the collective state of the molecules inside the system rather than the individual state of each and every molecule of the system. Now for that, we've got two major types of energies which are present in a system, which is kinetic energy and potential energy. The potential energy is due to two major forces. Number one is chemical energy. Sorry, number one is due to chemical bonding, which produces potential energy, and number two is physical bonding, physical forces such as intermolecular forces, which produce potential energy. Likewise, if we talk about the kinetic energy, it is basically the energy which is due to which is a result of motion, such that if the molecule is moving, then it possesses some amount of kinetic energy, which uh, causes it to move in the system, and that kinetic energy is what we call as the state. The kinetic energy is what we call as the energy required for the molecule to move, right? When the molecule is moving, it is having kinetic energy inside it. Now if we talk about temperature, what is temperature in actual? Temperature is basically, it is the average translational kinetic energy of a system. It is the average translational kinetic energy of the system. Temperature is the average translational kinetic energy of the system. Whenever we measure temperature, what we actually are measuring is that we are measuring the translational average translation kinetic energy of the system, that the kinetic and the average kinetic energy of all the molecules of a system basically define the temperature of the system. Let's suppose if a body is hotter, which is having more temperature, what does that mean? This means that that body is having higher kinetic energy than another body which is having lower temperature, having lower kinetic energy. Now if we talk about kinetic energy further, um, we need to understand the concept of further. Kinetic energy is what constitutes a major part of internal energy. So kinetic energy plus potential energy, or the total energy of a system present inside it, is known as the internal energy of the system. Internal energy of the system. Now um, in many cases, it's not necessary that the total energy of the system, internal energy of the system, is a sum of kinetic energy plus potential energy. There can be a possibility in a system. Let's suppose if we take ideal cases, whenever we are taking ideal cases, let's say we are taking the KMT, kinetic molecular theory. Kinetic molecular theory is based on is based on the case of ideality, such that it is based on ideal cases. That's everything happen. That's the gas molecules in KMT, kinetic molecular theory, are ideally moving without any sort of intermolecular forces. Intermolecular forces are zero, attractive forces are zero, and thus their potential energy is zero, due to which their kinetic energy is maximum, potential energy is zero. So if we consider ideal cases, in ideal cases the internal energy of the body is totally dependent on the kinetic energy, because potential energy is zero, due to which the internal energy is always equal to kinetic energy in ideal cases, in ideal cases, internal energy is equal to kinetic energy, right? So whenever we study thermodynamic processes, as we are considering KMT, we basically study that on the basis of ideal cases. So whenever we ask that if the internal energy of the system is increasing, what is increasing in that system? Then increase in internal energy is equal to the increase in kinetic energy in a system. We are going to mathematically prove it as well later on. So increase in internal energy is equal to the increase in kinetic energy. And if we in ideal cases, if we increase the internal energy, kinetic energy is increased, due to which the temperature is increased as well. So at the time of fever, when there is high temperature, the person is having high amount of internal energy rather than high amount of temperature, because temperature is a measure of the internal energy in ideal cases, but generally it is a measure of average translation kinetic energy, right? If we talk about absolute zero, at absolute zero, the kinetic energy of the system becomes zero and potential energy becomes maximum. At that moment, the internal energy of the system is completely dependent on potential energy, due to which we can deduce from this fact that temperature is completely dependent on kinetic energy in ideal cases, and temperature is completely independent of kinetic energy at absolute zero. So, sorry, temperature is completely dependent on internal energy in ideal cases, and temperature is completely independent of internal energy in absolute zero. So these are the two major MCQs, right? So this is a basic concept of internal energy. Hopefully you enjoyed the video. We'll meet again in another video.